Dear students, welcome to the world of electronics. Here I am going to discuss about the basics of electronics engineering. The syllabus is attached here. There are total of 6 paragraphs are there, or I can say there are total of 6 modules are there. The first module dealing with active and passive devices. This is only review only. LED working, applications, comparison of LED lighting and CFL lighting, full wave rectifier, diagram and its explanation, 5-volt power supply with a bridge rectifier and IC 7805, SMPS block diagram and advantages, integrated circuits, SMDs advantages, static electricity, precautions in handling electronic circuits. The next module is switches, on off switches, push to on, push to off, push to on off, SPST, SPDT, DPDT. Working and application of limit switches, proximity switches and relays. Third module is dealing with microcontrollers. Simple block diagram of 8-bit microcontroller and its application. And the next one is mobile technology, CDMA and GSM. Its comparison 2G and 3G technologies. Next one, inverter and UPS. Block diagram, comparison between inverter and UPS, online and offline UPS, battery selection of UPS and inverter. And the last one is electronic waste, e-waste, health hazards of e-waste. First, we are going to see the classification of electronic components. That is two type of classifications, active and passive devices. The electronic components or electronic elements are broadly classified into two types. The first one is active elements or active devices. Active elements. And the second one is passive elements. When the element is capable of delivering energy independently for a long time, or when the element having the property of internal amplification, then it is called active elements. First I will write the statement, then after that I will explain. When the element is capable of delivering energy for a long time means infinite time, or when the element having property of internal amplification, then it is called active elements. For example, the example for active elements are voltage source, current source, then transistors, op-amps. Op-amps means operational amplifier. In short, we will written it is op-amps, then generators. Okay, coming to the first example, here for active elements, I am written two definitions. Okay, coming to the first examples, voltage source and current source. Okay, for this example, the first definition is valid when the element is capable of delivering energy for a long time. Voltage source and current source are delivering energy for a long time. Okay, then coming to the another example, transistor op-amps. They have the property of internal amplification. So consider the transistor case. We can write the collector current IC is equal to beta IB. Okay, IB means the base current. Here IB is the base current is the input current, collector current is the output current. So here output current, collector current is beta times input current. So here internal amplification comes. So transistor is also an active element. Then coming to this expression, here the output current is controlled by the input current IB. So transistor, I can say current controlled transistor is an example for current controlled current source. Similarly, op-amp is voltage controlled voltage source. Okay, next example for active element is generators. All of you know that generator is generating the electric energy. So this one is electrical energy at the output side. The output energy is in the form of electrical. This one is generator. And the input side is mechanical energy. The definition, all the definitions of active element is valid in terms of electrical energy. So here also generator is delivering energy. So that I can say generator is an example for active elements. Then one more feature of active element is active element has ability to electrically control the electron flow. That means consider the case of a transistor. Here by varying the base current, I can control the flow of electrons so as to control the output current IC. Okay, next classification is passive elements. When the element is not capable of delivering energy independently, then it is known as passive elements. The element is not capable of delivering energy independently, then it is called as passive elements. The example for passive elements are resistor, inductor, capacitor, transformer, diodes, and so on. Okay. In the case of a resistor, the resistor is dissipating energy. When the current is flow through the resistor, it dissipates energy in the form of heat. So they are not delivering any energy. For in the case of inductor and capacitor, they are not delivering energy. During the discharge, they are delivering energy, but for a short time. So inductor and capacitor are the examples for passive elements. Then coming to the transformer. Transformer, all of you know that there are two type of transformer, step down and step up. Here I am writing one step down transformer. That means number of coils in the primary side is greater than that of secondary side. So at the primary side input voltage is V1, the input current is I1, and the output side is, or secondary side, the output voltage is V2 and the output current is I2. Okay, so it is a step down transformer. So I can say the output voltage or secondary voltage is greater than primary voltage, but the primary current is greater than secondary current. But in all these conditions, the power at the primary side, that is V1 into I1, is same as power at output side or secondary side, that is V2 into I2. So power at both sides are equal. So there is no energy creation or delivering energy in the case of a transformer. So transformer is also an example for passive elements. The next topic is light emitting diode, LED. A light emitting diode is essentially a PN junction diode. When the carriers are injected across a forward biased junction, it emits incoherent light. Most of the commercial LEDs are realized using a highly doped PN junction. So basically, a light emitting diode, that is LED, are PN junction diodes. It is working under forward bias condition. The symbol for light emitting diode is Yeah, this one is the symbol for light emitting diode. The arrow mark indicates that it emits the light. So this is P side, this is N side. It is working under forward biasing mode, means the positive terminal of battery is connected to P side of the light emitting diode, and the negative terminal of the battery is connected to N side of the LED. Or I can say, when the LED is said to be under forward bias condition when the voltage at the P side is greater than that of N side. So remember, the LED is working under forward biased condition. Then LED is an example for photo device, because it emits light. So I can say LED is an example for photo device. The next point is it is a heavily doped PN junction. Heavily doped PN junction. This I can write PN plus. The heavily doping is done at the N side, so that I am representing that is as a N plus, but the P side is moderately doped. Okay, so it is a heavily doped PN junction fabricated from fabricated from direct band gap semiconductors. This statement is important. PN junction LEDs are fabricated from direct band gap semiconductors. Okay, and before going in detail about LED, first we will discuss about the direct band gap semiconductors. So I will write the topic name direct band gap semiconductors. If the minima of the conduction band and maxima of the valence band occur at the same value of momentum, that is at k equal to 0, then such semiconductors are said to be direct band gap semiconductors. If the minima of conduction band and maxima of valence band occur at same value of momentum, the momentum value is k0 value, k equal to 0. Then such semiconductors are called direct band gap semiconductors. Okay, before explaining this one, first we will look at what is conduction band and the valence band. Okay, so valence band means it is the band of energy signals which are closer to the nucleus. An electron present in the valence band is called bound electrons because it cannot move freely when the external electric field is applied. That means they are bounded to the nucleus. They cannot move freely unless external electric field is applied. Then coming to the conduction band, it is a band of energy levels which are far away from the nucleus. An electron present in the conduction band is called free electrons or conduction electrons because it can move freely when the external electric field is applied. So, before explaining this direct band gap material, first I will write the expression for kinetic energy. All of you know that the basic expression for kinetic energy E is equal to 1 by 2 mv square. For in this scenario, m is the mass of electron and v is the velocity of electron. Okay, just I am multiplying by m with the numerator and denominator. So E is equal to m square v square divided by 2m. This can be written as mv all square divided by 2m. Then one more basic expression, the expression for momentum. Momentum is indicated by k, which is equal to mass into velocity, k equal to m into v. So the expression for kinetic energy can be rewritten as E is equal to k square divided by 2m. Okay. So when I am drawing a energy versus momentum diagram, x-axis is taken as momentum and the y-axis is kinetic energy. So the graph looks like a parabola because look onto the expression E is equal to k square divided by 2m. So this is an expression for parabola. So the energy versus momentum graph resembles parabola. Okay, this energy versus momentum graph is known as EK diagram. Okay, then I am going to draw the EK diagram of a direct band gap semiconductor. x-axis is momentum, and the y-axis is energy. The energy difference between the valence band and the conduction band is known as energy band gap, denoted by Eg. Then when we move on to the top side, the energy of the electron is increases. Okay, then going to the definition of direct band gap semiconductors. If the minima of conduction band and maxima of valence band occur at the same value of momentum, then such semiconductors are called direct band gap semiconductor. So in this figure, the minima of the conduction band, that is in green color, I am showing here my dot here. This one is the minima of the conduction band, then the maxima of the valence band are occupied at the same value of momentum. Okay, that's why it is known as direct band gap material. Okay, the examples for direct band gap semiconductor materials are gallium arsenide, then gallium phosphide are the direct band gap semiconductor materials. Direct band gap semiconductor materials are used for the fabrication of light emitting diodes. In direct band gap semiconductors, free electron is present in the conduction band can directly recombine with a hole present in the valence band. This is called direct recombination. That is, the free electrons present in the conduction band can directly recombine with a hole present in the valence band. This is called direct recombination. Again, I will draw one more Recce diagram for explaining this statement. An electron is occupied at the conduction band, and this is energy band gap. Okay, that the free electron present in the conduction band can directly recombine with the holes present in the valence band. That means when these electrons present in the conduction band combining with the holes present in the valence band, an energy is released. This energy I can E is equal to, I can write H into F, where H is the Planck's constant and F is the frequency of the incident light. When the electron returns to valence band, the energy will be released in the form of photons or light particles. Therefore, direct recombination is also called radiative recombination. Okay, then already I have stated that this LED is working under the forward biased condition. When the LED is in forward bias condition, the electrons are injected into the p side. The electrons are minority carriers in the p side, so This process is called minority carrier injection. But the Hole injection from p side to n plus side is very less because the n plus side is heavily doped as compared to p side. So the current is primarily due to the flow of electrons into the p side. These electrons injected into the p side recombine with the holes, and this recombination provides or results spontaneous emission of photons. So remember the one more point, in LED the spontaneous emission is happen. Whereas in laser it is stimulated emission is happening, but the LED the spontaneous emission is happening. Okay, so already I have stated that the free electron in the conduction band directly recombine with holes present in the valence band, and as a result of this recombination the energy is released in the form of photons. Only in the direct band gap materials when the recombination happens, the energy is released. Only in the direct band gap materials the released energy is in the form of light. Okay, that is the reason for direct band gap material is used for fabrication of LEDs. Then the energy of a released photon is written as h into f, where h is the Planck's constant and f is the frequency of emitted light. Okay, this is equal to h into, for f frequency I can write c by lambda. So h equal to c by lambda. Okay. For c is the velocity of light, which is equal to 3 into 10 raised to 8 meter per second, and h is the Planck's constant. H is the Planck's constant is equal to 6.63 into 10 raised to minus 34 joule per second. Lambda is the wavelength of the photon. Then during this direct recombination, the energy of a released photon will be at least equal to the energy band gap Eg. During the direct recombination, energy of a released photon will be at least equal to Eg. That is energy difference between valence band and conduction band. So by the expression I can write the energy of the emitted light is Hc divided by lambda, which is greater than or equal to energy band gap Eg. So rearranging this equation, this I can write Ec divided by Eg greater than or equal to lambda. So lambda is less than or equal to Hc divided by Eg. Okay, Eg is the band gap energy in joule. Okay, now I am changing this unit of Eg into electron volt. Electron volt also a unit of energy. So in order to convert the band gap energy in joule unit into electron volt, I have to multiply it by the electron charge. So this I can write lambda is greater than or equal to hc divided by the band gap energy unit I am changing from joule to electron volt by multiplying electronic charge 1.6 into 10 raised to minus 90, where EV is the unit of energy. Okay, then I am substituting for values of Planck's constant H, which is 6.63 into 10 raised to minus 34 into then c is the velocity of light, value is 3 into 10 raised to 8 divided by band gap energy into electronic charge 1.6 into 10 raised to minus 90. So substituting all these values, we will get lambda less than or equal to 1.24 micrometer divided by Eg. The micrometer is 10 raised to minus 6 meter. Okay, so this is the expression. The wavelength of emitted photon is less than or equal to 1.24 micrometer divided by band gap energy in electron volt.